Don't breathe.
So I watched an episode of How I Met Your Mother yesterday.
Oh, you did.
I did.
That's just his fault, by the way.
And
The super old
Barney
ones?
used like 12 math words in a matter of like 30 seconds.
Who did?
It was
What
so
math
awesome.
word?
Barney. I don't remember them all. I have
Oh,
to
is
find
it the one
clip.
where he's like, if E equals
Oh,
A
yeah,
times
yeah,
one? Was it the drug train?
The drug train, yeah. And then,
Yes!
Yeah, and then Ted's like, it's been here all along. He circles the whole thing.
Yes!
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 Yeah.
I was like, oh my gosh.
It's all, it wasn't even that. They were just random words.
No, they made sense. No, when they were in the bar talking about it, and yes, right before that scene that you're talking about.
This crap, this is on camera.
On the board.
He's like, it's just how I met your mother.
I was talking about getting drunk at the bar and it's on camera.
I don't.
It's not real life. And this one,
I don't like you using that term around me. I respect my mother, and
okay.
yeah.
This video is not going to go on YouTube if you turn this inappropriate. All right, number 40. So we're talking about what does the graph of the derivative look like if the function is increasing, because we're told in part A that our function is increasing. Evan said that our function or our derivative is positive. So on a graph, what does it mean for something to be positive or to look positive?
It's gonna be the first one.
Y value first.
It's going to be in the
Say
first
first.
or second, right? It just has to be above the x-axis. So we do know that we can eliminate one of our graphs. So if we're looking at part A, f of x is increasing, which graphs could it be?
2.
It could be 2 or 3,
2 or 3.
because both of those are in quadrant 1. Okay, and then, so to eliminate even further, again, we're looking at the graph of the derivative. When is a function concave up? So we want to know that it's increasing and concave up. When is a function concave up?
The tangent lines are below.
Okay.
When it goes from increasing, it goes from decreasing.
When the second derivative equals 0.
Nope.
Yes.
Those are inflection points, huh?
Concave up when it goes from increasing to decreasing.
And you have the concave up on the original function?
How do we get concavity?
Integral.
By failing a test, your grade goes like this.
Second derivative.
Second derivative. Welcome. Welcome to class. How do we get concavity?
Second derivative.
Okay. So when is a graph concave up?
When the second derivative is greater than 0.
When the second derivative is positive. Okay? We're looking at graphs of first derivatives. We are down to either graph 2 or graph 3. These are the first derivative. How are we going to know if the second derivative is positive or negative?
Sign of prime.
No answer.
Thinking in the prime.
Repeat the question.
What does that even mean?
What does that mean?
I didn't hear the question.
If this is the graph of the first derivative, how do we determine if the second derivative is positive or negative?
Well, the second or the third one's decreasing, so would the next one be negative? Like the second derivative be negative?
Yes! So, can you say that again?
It's decreasing, so then second derivative would be negative?
Right, because the derivative of this graph, these are all decreasing. So the derivative of this graph is negative. Yes?
Yes.
The derivative of this graph is the second derivative. This one right here, the derivative of this graph is what?
Positive.
Why?
Because it's increasing.
It's increasing, this graph is constantly increasing, and so the derivative of this graph would be positive, and the derivative of this graph is what? I'm sorry. In relation to our original function, the derivative of this graph is the second derivative. I can see the blank stares happening right now. So the derivative of this graph is positive, that means the second derivative is positive. If the second derivative is positive, what does that mean about our function?
It's negative.
It's
It's concave up. If the second derivative is positive, it's concave up.
When did we learn this?
4.1. When
Yeah, only a week ago.
A week is a long time.
So, from the graphs that we're looking at, we are looking at first derivatives. We want to know when our function, or which of these shows a function that is increasing and concave up. We know that these two represent an increasing function. Why? Why do we know that these represent an increasing function? They're above the x-axis. The first derivative is positive. Which of these shows a function that would be concave up? The middle one.
The middle one.
Why?
Because the second derivative is positive.
Because the second derivative, the derivative of this graph would be positive.
Could you estimate, like, if you're on this rate, can you estimate
Okay, so for part A, f of x is increasing and concave up. Which graph represents that? Graph 2. Part B, f of x is decreasing and concave up. Which- Why 1?
Because it is not, it's deep, because it's below the x-axis.
So because this function is below the x-axis, then my function must be decreasing, because this means that my derivative is negative.
I'm still having trouble finding the relationship between derivatives
Makes sense.
and functions.
On a graph. Okay, I'll get an insight. We'll go through a specific, this I don't think is gonna help, this is too big. I'll get a specific example.
And you said that it's concave up if the second is positive? Okay.
Yes. And the second derivative is going to be the derivative of the first derivative.
Of like,
Which,
so like if you took the function of whatever that graph was and then you did that, it was positive?
yes.
But we can do that by just looking at it?
Because visually, what is a derivative?
Thank you.
Forget the word visually, what is a derivative? It's the slope of the tangent line. So if I make a tangent line right here, is my tangent line positive or
Oh, okay,
negative?
it's gonna be negative, so then
It's gonna be positive.
Oh.
The tangent line is gonna have a positive slope.
Okay.
On this one right here, if I draw a tangent line,
That'd be negative.
the tangent line is negative, so that means the derivative of this function is negative. The derivative of this function is the second.
Wait, those are functions?
Yes, every graph is a function.
They're not derivatives of a function.
These are derivatives of a function, but a derivative is its own function. It's just that it's related to another one.
She said the second is negative.
Yeah.
I left all my stuff suspended.
No, it's positive, it's concave, and negative, it's concave.
All right, any questions on this? If I'm going through an example of finding maximums and minimums with a graph, or talking about maximums and minimums with a graph, what do you think you're going to see on the test tomorrow? Good, good.
So might be one of the problems.
Might be.
Or
Maybe.
half of one.
Perhaps.
Get to one.
We'll see. Okay. Next question. Next topic.
Can I get a drink of water?
Section. Whatever you want to call it. Hurry back. Finding maxes and mins. Stop talking. With an equation. Specifically looking at different intervals. So let's look at numbers 31 through 38. We'll do a couple examples from this. I'll start with number 32. The instructions are to find the extreme values on the interval. Our function that we have here, f of x equals 6x to the 4th minus 4x to the 6th. We have a closed interval here from -2 to 2. Okay, keep in mind that if we're talking about a closed interval and we're looking for extreme values, then we have to check our endpoints because we can have an absolute max or an absolute min at our endpoints if we're just looking at an interval. That's where the absolutes come into play, is when we're talking about intervals. Okay. So I want to evaluate or find extreme values of this function on the interval -2 to 2. What's my first step? What am I trying to do here?
Find the critical point.
Why am I finding the derivative? For what?
See for critical points.
Critical points. So I'm going to have critical points here. So I start by deriving this function. When I derive this function, what do I get?
24x cubed minus 24x to the fifth.
Whoa, what's happening here?
She just got
Jinx,
using
y'all.
that rule.
Miss
you
Crab,
think
have
that
you
it's
seen
zero?
How I Met Your Mother with the Jinx?
Okay, we're going to keep going with this derivative here. So critical numbers, how do I find critical numbers? Set it equal to 0. So I have 24x cubed minus 24x to the fifth equals 0. How do I solve a problem that looks like this?
You divide
Comes back to
24.
Factor would be the proper word, yep. What do I take out of this? What can I factor out?
X cubed.
If I take 24x cubed out of this, then what do I have left?
X
One minus x squared.
Huh?
squared minus uno.
Now what?
You
Set both
divide
parts
by
equal to
20.
0.
split them
Set
apart.
both parts equal to 0.
Set them equal to 0. What is this one gonna give me?
0,
What are those gonna give me?
1.
And negative 1.
Negative 1.
Plus or minus 1,
Yeah, this is square root.
because it's a square root.
I don't get what we just did.
Bro.
What was that
If you leave the
for?
class, then I don't know what to tell
What
you.
was that for?
You're finding critical points, so you have to find a derivative
Oh,
of this.
I know how to find a critical point.
Okay,
I'm sorry.
extreme values.
Yes. Yes, those are your critical points.
These are all of my critical points, so this is where I could have extreme values. Let's break these up into maxes and mins. How do I determine if it's a maximum or a minimum value?
Plug
Put it on the
in
number
derivative.
line.
Plug it into the
Put it on
original
the number
function.
line.
And you find the highest and lowest answer you get.
Number line, right?
Oh, yeah.
And interval.
That works on the interval ones. When we're just dealing with intervals, we're just evaluating our function at each of these points.
The original one,
That's
that's
everything minus interval.
It's the original function, right?
Yes.
Yep,
It's the 24. Hey, why are you minus 24?
So it's a 6
Okay.
set.
Oh, because, okay, I see.
Yeah, 6
If
sets.
it
So
was
that's
your interval, it would be like
your-
Why are they talking so much?
It's crap, it's the original function or the derived one? Original.
this is only gonna give us absolutes, and then we're gonna have to go through.
But that's fun.
Let's find locals.
Absolute maximum and
Oh, does
minimum.
it say extreme values? That's all.
Wait, what's?
And the absolutes are going to be the highest and lowest ones, right?
Correct.
And then to find the locals.
I'm a little concerned that you're not taking notes right now.
Are we supposed to?
I mean, don't you think to study tonight, it might be good to like have this?
I'm not going to have time for that.
All right.
Yeah, I'm just writing it down.
No,
You have time right
You don't
now.
have to write
Huh?
stuff down.
Should we do something?
I'm paying attention.
I just don't want to hear any whining tomorrow.
Well, I'm going to fill it in.
F of negative 2, what is it?
Negative 162.
Do we agree? 'Cause I'm not checking this, so someone should probably check it.
You plug it into the original function or the derivative?
Original function.
Negative 162.
F of negative 1?
Positive 162.
You get the same answer.
That doesn't make sense. That'd be 2.
It's 6 minus 4 equals 2.
Plug in a 1.
Oh,
How
no,
is this
Never
negative?
mind. Never mind. Yeah. never mind.
How do you get 162 with a positive one?
Yeah, but we'll think about that.
What if I plug in 0?
0.
0.
What if I plug in 1?
2.
What if I plug in negative, or 2?
It should be negative 1.
Should be the same thing.
The
Assuming
first
you
one
get
I'm wrong.
this
I
one.
got
Negative
negative
352.
352.
You did it wrong.
What?
I got negative 352.
Oh my word.
Okay, so since those are two the same, are those both going to be local minimum? I mean, absolute minimum.
Wait, did you
Wait,
subtract
does the
what you
answer
had?
matter or does, isn't the negative and positive not matter one?
Huh?
Does the answer matter? Negative also does not matter. Did you get the points?
Good.
The answer does matter.
I got negative ones.
Very good.
Remove.
You
Negative 160?
Yeah. Is that
I
right?
got 160.
I got 160.
Yeah.
Yeah, I got negative 160 as well.
Yeah.
I'm up there. Here.
Alright, regardless. Where is my absolute maximum?
2.
Yeah, it's 160.
So max. Where's my absolute minimum? These are max. I should have put those in a different color. Okay, so my maxes are at plus or minus 1, and then y is equal to 2. And I have minimums at plus or minus 2, where y is equal to negative 160. Keep in mind that these are absolutes because we're talking about a closed interval. That's why we're looking for these absolute values.
What do you rate
Are those
this
the
girl?
same ones you can play?
You said don't erase?
Yeah.
So you add, subtract 1.
What's on that?
It's a monster. We
Ew.
discussed in fourth block how it's kind of the opposite of a unibrow because instead of having one eyebrow and two eyes, it has two eyebrows and one eye, which I thought was kind of weird.
I don't think that's very good.
Why?
I've
Why would it have?
So it's a uni.
Why would it have two eyebrows if it only has one eye? It only needs one eyebrow. It just needs one over the one eye.
Why would you judge it that way?
It's
I
craft.
guess I'm a judgmental person.
Why do we need 5
It's
toes?
only
when we
notes,
only
but there
have
isn't like one note that will do it together.
What?
I don't know.
Did you have a question, Sam?
No.
Okay. All right, stop talking.
Miss Crafton, what is 0 classified as?
What? Nothing.
Nothing?
It'd be a local minimum.
No. Yeah.
It could be a local max. Is it a
Wait, I'm
local
so
max?
confused
Yeah,
about
it'd be a
local
local
mins and
minimum.
maxes.
Too, I really don't understand that.
Local and absolute, the difference between local and absolute, like it's individual, because every time I do a homework and I think something, it's completely different as to what I'm thinking.
Okay, so let's do an example where we're dealing mainly with local ones. Absolute, you're focused on when you have a closed interval.
So absolute is.
Graph of it so she can see it.
A graph of this function.
Yeah, not necessarily on a calculator, just, you know what that would look like, right?
I mean, I know what the sixth, how many,
I love that M.
In local,
Yeah, it would look
open?
like an M.
because it's gonna go
It doesn't matter if the function is closed or.
like that.
Yeah. So,
Esmeralda?
What's her
that,
name?
that's what that interval would look like. You look at it? That's the interval. So you have the max where it's at the highest and the minimum where it's at the lowest, but the 0 is where it dips down a little bit and then goes back up.
I'm a little salty with Chris right now.
It's gonna be,
Sorry.
okay.
You know
Do you understand what he's saying to you? Thank you, Chris. Do you understand what he's saying?
Like,
That's what we just did. No. Okay, listen, stop talking. Absolute max and min values only happen on a closed interval. That's when you're going to be asked about absolutes. Because endpoints can be considered absolute extreme, like maxes or mins. Local maxes and mins come into play when you're just looking at a function and you're trying to determine if there's some kind of point that looks like this where it goes up and goes back down, or where it's going down and it comes back up. Those are local. The difference when you're looking at a graph is that an absolute is the absolute highest it ever goes. The absolute minimum is the absolute lowest it ever goes. If I'm looking at all of these points here on a closed interval, the absolute lowest it's ever going to go is negative 160. Because I've tested the only points that matter. The only points that matter for maxes and mins are critical numbers and endpoints on an interval. Okay?
To find local max and mins, is that where you put the number on the number line?
Yes, that's what we're going to do right now. Okay, next example, I'm gonna look at number 29. 29 says g of theta equals sine squared theta plus theta.
Hiccup. No.
And we're being asked to find the critical points and determine whether they're mins, maxes, or neither.
Is theta generally used to represent,
It could be like
a degree, like a, so like, it generally isn't like represented as anything else?
It's representing an angle, which might be given to you in radians. In calculus, it's going to be given to you in radians. All right, so I'm looking for critical numbers. How do I find critical numbers? Okay, I'm deriving this function. Sine squared theta, how do I derive this?
You put like sine.
I have to use a chain rule. What is the outside function for this?
Squared.
The squared, so how do I derive that?
You bring the squares in front, and then
Keep the original
keep the original function.
Wait, don't you write the original function?
I just did, sine of theta.
Multiply.
No, but you keep sine squared.
No, but
Well,
you
I
go
just
n minus
got
Oh
one.
my
down
goodness,
and
the homework is
subtract.
freaking stupid.
Then you take the derivative of sine of this.
Ridiculous.
What you get cosine. Plus one.
All of these side conversations are really annoying me, because then you're going to ask me questions, and then I'm going to be even more annoyed.
Cosine
Isn't
theta.
that a double angle?
Plus one.
Yeah, sine of 2 theta equals
Do not group. Okay, I see.
So the derivative of this is this double angle of sine. It's kind of interesting. Sweet. I want to see that on the graph. That's what I'm going to do.
Wait,
What?
you should probably know this.
What?
So why did you get cosine?
Because I derived the inside. The inside is sine of theta, and the derivative of sine of theta is cosine.
Okay, I got.
You have to use the chain rule for that?
She just.
Literally, that was like the first thing she said.
Damn.
What's theta on here?
Since X.
I think that's theta sign.
There's
But
more
you
than
said-
just sine inside the function.
You're good?
Isn't
sure?
it a trig identity?
Okay. Huh?
Is it a trig identity?
Yeah, it's a double angle identity.
Do it.
All right, plus the derivative of theta. What's the derivative of theta?
One.
Do it.
1.
One. One.
Okay. We actually have to use this double angle identity.
Yay.
So when we set this equal to 0, if we try and solve, like we have two different trig functions, and so we're not going to be able to solve with those two trig functions in there. And so 2 sine of theta, cosine of theta, stop talking, please listen. This is an identity that I can almost guarantee you're gonna see on the AP exam. This is like the most basic identity in trig. So 2 sine of theta, cosine of theta is equal to the double angle of sine. It's equal to sine of 2 theta. This was an identity you would have learned in pre-calculus when we're talking about double angle formulas. It's one that you need to know and recognize. So sine of 2 theta plus 1. And now we can solve for this. Sine of 2 theta is equal to -1. We use the inverse sine. So 2 theta is equal to the inverse sine of -1. And what is the inverse sine of -1?
Zero.
Where is sine equal to -1?
Oh.
At 3 pi over 2. Then we divide by 2. And when we divide by 2, we're going to get theta equals 3 pi over 4. Yes.
So you said this is gonna be graded on,
Standard.
the standard? So, if we're doing a problem, and we go through like the first half, and then we get stuck, are you
Still
gonna,
have to get the
is that gonna be 0? Well, but knowing the process to get to like half of it, I'm gonna fail.
Then we
It
put
doesn't
it
mean
in-
you get points for effort. You still have to know how to do stuff.
So don't we put it in the original?
Also,
Max
what about
max
doesn't
number?
matter.
What?
Plug into the original function to see if we get maximum number.
Yeah, can you give us a participation grade?
Oh my gosh.
You really should give us participation grade.
No, this is not kindergarten.
We have participation points in A push, so that's
So
kindergarten class.
you can do that.
I like the way you do test correction.
Okay, we are continuing this problem. What is our goal? What are we trying to do?
Find a maximum.
Find maxes and mins. I have a critical number here. How do I determine if this is a maximum or a minimum?
Plug it into the original function.
If I plug it into the original function, it's just going to give me one value. And I have nothing to
Set
compare
equal
that
to
value
0.
to. What do I have to do?
Set up intervals.
I have to set up intervals. Why am I setting up intervals? What am I trying to find?
When it
When
goes
it's-
from increasing to decreasing.
Or decreasing.
Yes. So going from negative infinity to 3 pi over 4, what's a value in there that's going to make this easy?
5.
Easy.
Pi.
Easy.
0.
0. Let's plug in 0. So sine squared of 0 is what?
0.
0. Plus 0.
I'm seeing you.
It's 0. Wait, it is 1.
Yeah, it's one.
It is 1.
Sine of 0 is
It's
not
1.
1.
Put yourself up.
What did I just do?
Hey, calm down.
So Miss Coffee had this problem the first
So it's
day.
positive.
I think it's one.
Sine of 0 is not 1. Sine of 0, there's a unit circle on my board. Sine of 0 is 0.
No.
Yes. JJ,
Why are you saying
Oh
no?
my goodness.
What is your
Oh my
yeah.
gosh, I have to plug it into the derivative. I'm trying to figure out if the derivative is positive or negative, not if the original function is positive or negative.
No, she said the original function just needed one thing.
Oh, okay.
I plug it into
One.
the derivative.
Equal what?
So sine of 2 theta when I plug in 0 is 0. 0 plus 1 is 1, so this is positive. Because I'm trying to figure out if the derivative is positive or negative. Because if the derivative is positive, my function is increasing. If the derivative is negative, my function is decreasing.
Oh, so like plugging into the original function is just for gas.
Like it's only on the closed interval?
Yes.
Where'd you plug it in this time?
Oh,
The derivative.
collard greens.
Show it.
See, Vaughn, I don't criticize you when you ask a question.
I'm gonna plug it in. I'm gonna plug it in right here. Sine of. Are you listening?
Oh no, Sam's only talking to me nuts.
Sine of 2 theta plus 1. This is my function.
That's the one you plug it in.
If I plug in 0, I get sine of 0. And sine of 0 is 0. 0 plus 1 is 1, so it's positive on that interval. Okay? Then from 3 pi over 4 to infinity,
Pi.
pi is an easy one because when you plug in pi here, you're evaluating sine of 2 pi. What is sine of 2 pi?
0.
Sine of 2 pi is 0, plus 1 is
Positive.
positive.
So it's even.
So there's no local max or min here.
You think the low is increasing?
So you found theta, these theta intervals. This is a critical number.
Can we do inflection from this?
We will get there. Have a list. All right. Any questions on this? If I'm giving you an example with trig functions, what do you think you're gonna see tomorrow? Probably see trig functions. Okay, the next question I want you to look at is number 39. It tells you to find the critical points and extreme values of f of x equals the absolute value of x minus 1 plus the absolute value of 2x plus 6 on the interval from 0 to 8.
I didn't get the sheet that we're working on.
Oh, sorry.
I didn't realize we were working on it.
Okay. Please listen. Whenever we have absolute values, what do we have to do with those? We have to split them up as piecewise functions. So here's what's going to happen. We are going to have a piecewise function here and a piecewise function here. And because of that, we are going to come up with 4 different functions. Let me explain how. Okay? Starting with this one, x minus 1. How can I rewrite this as a piecewise function?
Just negative x minus 1 parentheses, that parentheses,
Okay, when is it negative x minus 1?
when x is less than 0.
When x is less than 1, because we have a shift here.
I always forget with the shift.
When is x minus 1 just x minus 1?
It's greater than or equal.
Greater than or equal to 1.
Wait, I'm confused. Why?
Because it's absolute value, and absolute value always gets written as a piecewise function.
Wait, why 1?
Because this shifts it side to side. It moved it over 1.
So it has to be less than 1?
Yes.
It's negative.
That's a point where
Because
this...
that's where it's going to be 0
also be-
if it's not. Okay.
Okay, then we have... So let's think about this individually. I'm going to put this in a box. Okay, then we have this piecewise function. We're going to think about this piecewise function individually.
Oh, that means this is going to be on the test.
So how do I write this piecewise function?
Negative 2 or negative 2x minus 6. X is less.
Okay, so when is this negative?
When x is less than
3?
Less than 3.
I said
3 or whatever, because if you put 3 in, it's negative.
less than 3.
How did this shift?
Oh, it's plus.
I less than 3
Oh, it's gonna
you.
be when it's less than negative 3.
Let's graph this. Yeah.
Why wouldn't that be x less than negative 4 or greater than negative 4?
Because the shift is opposite of what you saw. So it moved over. Okay, remember? Guys, everything I do with these piecewise functions and absolute value is visual for me. I'm imagining that v, because that's where this piecewise function comes from. Because I have a linear function going in one direction and a linear function going in the other direction.
Sorry.
This one's going negative, this one's going positive. That's where this piecewise function comes from. So I imagine this v, which is just the absolute value of x, and as soon as I put x minus 1, I imagine this v, which moves over to the right, 1. Because if it's inside of my function, it moves opposite of what we see. We talked about that in pre-cal with transformations, and you should have talked about that in other classes with transformations. So I am imagining where the point, the vertex of that v is, and if I have moved my graph over 1, the vertex is now at 1. That's now the splitting point for this v. Does that make sense?
Yeah.
Okay, when I get to this one, this v has 2 types of transformations to it. Okay, the first one,
So it's negative 3.
oh no it doesn't. It's negative 3, yeah. This on the inside, okay, I was thinking about that wrong. I was thinking this more on the outside, but it's not. This moves your V or your vertex to the left 3 spots. If we're, I don't want to say solving for x though, because then, I guess that is what you're doing. You're solving the inside. You're setting the inside of the current,
Absolute value.
thank you, absolute value bars equal to 0. And that point is the vertex of your V. And the vertex is what splits up these linear equations. Yes.
What is that split from?
The inside should be set equal to 0. Yes. The inside of the absolute value bars. If for some reason this had a +1 at the end, you don't want to set that whole thing equal to 0. It's just the absolute value bars. Did you miss that one?
Yeah, what is that?
Do you guys listen to anything?
You were talking directly to them.
Literally.
Push your left,
Okay.
left.
Absolute value. Ew. Okay, so when is this negative?
When x is less than -3.
-3, and when is it positive?
When x is greater than or equal to
Okay. So keep in mind that we're taking this absolute value and it's being added to this absolute value. Whenever we're talking about absolute value functions, they're split up with these piecewise functions here. So from the interval, I'm starting at 0 because they've given me an interval of 0. From the interval 0, oh, this doesn't even matter. It is only going to give me 2. 0 to 1, because that's where this one changes. 0 to 1, I have -x minus 1 plus 2x plus 6, because this one is a positive as long as x is greater than or equal to -3. And if we're at 0 and beyond, we are greater than or equal to -3.
Yeah.
Does that make sense? I'm going to be able to ignore this part, because we're never going to use x less than -3, because we're on an interval from 0 to 8.
What about x is greater
What
than
about x is, yeah, what about x is greater, or x is less than equal to x is less than 1.
We're not even there yet. I'm talking about this first one. So I can write this as a piecewise function where I have -x plus 1. All I did was distribute this negative. And it's being added plus 2x plus 6 as long as x is less than 1.
Is that a positive G?
Hold up.
It's just both of them because they look negative.
This plus this is the function. The function gets split up, or absolute value gets split up because it can be written as a piecewise function.
Oh, so there's different possibilities of different
Yes,
combinations.
there's different possibilities on different intervals.
I've sort of certain.
Oh.
So it's going to be this plus this as long as x is greater than 1. So from 0 to 1 is what
Why
I'm
did you
looking at.
cross that line?
Because I'm never going to use it because I'm only on the interval 0 to 8. And 0 to 8 is never going to be less than -3.
Okay.
Are you guys understanding how to manipulate these absolute value equations? No?
Yes.
Question about it? Lost? No words to it? Huh?
What did you do?
What did I do?
You said it had as long as x is greater than or
Sorry, less than 1. Then less than 1. So from 0 to 1, I'm using this part plus this. Because my function is this absolute value plus this absolute value. I'm not changing what my function actually is. I'm just splitting my function up because of the absolute value bars.
Is that a math joke?
Man made a math joke.
Okay. I'm just gonna keep going then. if x is greater than 1, so on the interval from 1 to 8, I'm using this part, x minus 1, plus the same second part, because the second part's not changing. So plus 2x plus 6, as long as x is greater than or equal to 1. I can simplify this function. Negative x plus 2x is x, 1 plus 6 is 7, and then x plus 2x is 3x, and negative 1 plus 6 is 5.
What do you do with the x is greater than or equal to -3?
Nothing.
You just give it.
It doesn't matter because I'm only on the interval from 0 to 8, and this is not changing from 0 to 8. It's going to be this part of it the whole time.
Oh,
Does that make sense?
yeah.
I should never took calculus.
So this right here, if I plug this into a graph, is the same thing as this being plugged into a graph. It's going to give me the same graph.
Is it just breaking it down more?
It's breaking it down to be derived because, I mean, I suppose we could have derived each of those individually. Absolute value is on the test, which is why I'm refreshing your memory on how to get through absolute value.
So that's the answer?
No, we have to find critical points. That's the function.
So x equals -7, x equals -5.
What?
You said find critical points, so
This is my function, this is not the derivative. Okay, to derive absolute value has to be written as a piecewise function in order to derive it. It's how absolute value works. So you write it as a piecewise function and then you derive each piece. So the derivative of this function, for the top part right here is what?
1.
It's 1 as long as x is less than 1. So your derivative is just going to be a straight line from 1 and then to negative infinity, so in the negative direction. And then the derivative of 3x plus 5
3.
is 3. So you're just going to have a straight line from 3, or from 1 on at 3. This is the derivative of this function. If we're looking for critical numbers, what are we looking for? Or
It doesn't exist.
when it does not exist. At what point does this derivative not exist?
There.
How do I do this? No, it exists at 2.
Because absolute values these will always get 1. So one thing either.
It's crap.
What?
When it
A derivative?
exists because when you have absolute value, it's gonna get you a positive number no matter what.
I keep mixing this up with continuity. But it's not differentiable at 1. Right, the derivative doesn't exist at 1.
Is this what it
Oh,
looks like?
because one is
It's greater than what?
because one is not x. That's
Can you plug that into this?
Is this what it looks like?
Freaking horse.
One of those has to be close.
Oh, okay.
That's what the derivative looks like.
Oh, I don't know what's happening.
Is that better?
We've been on this problem way too long. Ew, has been.
What?
What do you guys do after school? What do you do after school?
And we're gonna buy anything. We have some good stuff.
Okay, if our derivative is not continuous somewhere, our function is not differentiable at that point. Because we have a jump discontinuity right here at 1, because it's going to jump from 1 to 3, it is not differentiable at 1.
Okay.
Does that make sense?
Because
This is what your graph looks like. It goes down this line, and then it's got this corner that then goes up from there. That's what makes it not differentiable.
it says that 1 is, it equals 1 when x is less than 1, but 1 and 1 is the same, right?
Huh?
But it says 1 if x is less than 1. Because don't you plug x into 1, or 1 to x there? Because then 1 will not be less
No,
than-
these are the y values. This derivative is just a straight line. We hold that up. That's what your derivative looks like.
Oh.
3 when x is greater than 1. What? Huh? Yep, I plugged in that one. Okay, if nothing else, I want you to be reminded that you have to set up absolute value as a piecewise function. The question on the test is not there.
I know, because they're micro, is that the
It's not even differentiable. So,
It's not differentiable. What are we gonna do with it? I don't know.
because in order, the extreme value theorem, you have to have a differentiable function.
So we,
And it's not differentiable.
Oh,
So there is
low-key,
no-
still like
we just
that.
write does not exist.
Yeah, but it's continuous. The function's continuous, it's not differentiable everywhere on the interval. So there's no, you can't use the extreme value theorem. No, you wouldn't be able to find it.
So can we write
Extreme values, this is the one where, we looked at the graphs where it was like discontinuous. So it'd like go up and then there'd be another one up here, here, and then it'd go up to here. So it had a maximum at the end of this interval, but it didn't, or it was the other way around. It had a minimum, but it didn't have a maximum because of the jumps.
Oh, okay.
That's what's happening on
I
this
wouldn't do
one.
that. Because
That's what your question is. The point is, guys, the reason I took this was because I was just thinking that we would review absolute value. Please understand that you're going to have, stop talking, an absolute value question on your test tomorrow. You have to know to break it up and derive it from there. Okay, this extreme value, or you cannot use the extreme value theorem if it's not continuous on an interval. We talked about that when we discussed the extreme value theorem. You may want to go review that just a little bit. Understanding that all those theorems work under certain conditions, and so I would just review those conditions that we talked about. Okay, we are moving on to the next question. The next topic you need to remember, let's look back at number let's do number 51. It's asking you to graph a function.
Oh, is this the thing where you find the domain and the
Yep. Okay, here's what we're going to do with this. There is not a question on your test that says graph the function. Okay, it's not there. However, all of the steps that we use to graph a function are on your test. So that's what we're going to review, are the steps that we would go through. The first step being the domain. We need to identify the domain of this function.
It does not equal.
Okay, x cannot equal -1. Why?
Because it would make it undefined.
Okay, because then you'd end up with a 0 in the denominator, and we can't have that. So this function is going to exist everywhere except for where x is equal to -1. The second step. I don't remember these steps for granted.
How do you just determine the intervals?
Wait, is this the curve sketching?
Yes.
Yeah, find the intercepts of f is one.
Okay, so x and y intercepts. How do I find the y-intercept?
Set x.
Set x equal to 0, so where's my y-intercept?
0.
If I plug in 0 for x, I'm going to get 0. How do I find the x-intercepts? Set y equal to 0. If I set y equal to 0, I'm only looking at the numerator, and that's going to be at the same point, 0, 0.
Okay, and behavior of x.
So x and y intersection.
End behavior? Okay, end behavior. How do we get end behavior? I'm just going to tell you that this is the part you want to pay attention to for tomorrow's test.
That I'm gonna fail.
Limit as approaches infinity.
Yes, we're finding limits
Oh, what? Yeah.
as x approaches infinity
No way.
Okay, Thursday, guys.
Nowhere.
of our function, x to the third plus 1. What is this finding for us? The limit as x approaches infinity of a function.
Horizontal line.
It finds horizontal asymptotes. So how do I evaluate the limit as x approaches infinity of a function?
You divide it by the greatest
Divide by the highest.
exponent.
Divide by the highest power
The denominator?
in the denominator. So this is x over x to the third divided by x to the third over x to the third plus 1 over x to the third. And then what do we do with this? What equals 0?
Ones with an x cubed on the bottom and a variable on top.
Anytime you have a number on top and a variable on the bottom, it goes to 0.
So it's all 0.
So this is 0. This is 0. This is 1.
Which
Because x to the third over x to the third is 1.
I didn't see the x to the third.
0 divided by 1.
So 0 over 1 is going to give me 0, which means I have a horizontal asymptote at y equals 0.
Does it?
4 is the asymptotes, right? Vertical and horizontal.
Yeah.
Marla?
So just need to find a vertical.
Okay, so we already found our horizontal asymptote with end behavior. Stop talking. I need to know if there's a vertical asymptote. When do I have a vertical asymptote?
When the
-1.
denominator equals 0.
When the denominator equals 0, which is at -1. So there's a vertical asymptote at x equals -1.
Ew.
What's the thing right after end behavior? The H horizontal. Oh.
That's the at.
Next one is determine if the intervals are
I didn't finish it, so I got 30 seconds.
Okay, and then we look for increasing, decreasing intervals. How do we find increasing and decreasing intervals?
You
plug in.
Gosh, I don't
Critical
remember.
numbers, set up intervals, figure out if it's positive or negative.
So we have to do the
Quotient rule.
Miss Kraft, this is like ancient.
Well, we're gonna stop here.
I don't even remember this.
or not.
What?
We are gonna stop here.
What 4 what is this?
¿Por qué?
anything, it's just sketch and graph.
Sketching a graph came from 4.5, but
What did all that other stuff come from?
We didn't write.
No, we have 4.5.
Ms. Cross, these are really difficult.
Okay, what did I just say to you before we started this problem?
That is gonna be.
We are not sketching graphs on the test. And then what did I say in the middle of the problem?
We're writing
Pay attention to what?
And behavior.
The end behavior. Okay, moving on.
Yeah, so end behavior, we just limit that. And then you set that equal to 0.
Hurry back.
I don't know, I'm a failure at life.
Alright, I want to move back to.
Say I have confidence.
What is confidence?
Okay, I'm not going to spend time today on antiderivatives. Okay? Because we
I
did
love
that yesterday.
antiderivatives.
But listen, 71 through 84, that notation that you see there, that's the notation for an integral. That is an antiderivative. It's asking you to find the antiderivative of that function. The dx at the end of it goes away, or the d theta goes away when you antiderive.
And then you
Okay.
plus c.
And then there's a plus c at the end because it's a general integral.
So when there's that symbol, it's anti.
Yep,
Optimization.
that's what we're gonna do. So that's why I'm gonna give this overview real quick. 85 through 91, also asking for antiderivatives, and it's giving you the initial condition to get rid of the plus c. So remember, we had to solve for c.
That was easy though.
Okay? So I want to point those out because the notation is different than what we saw yesterday. But it's the same thing that we were doing. Okay? It's giving you the derivative and wants you to antiderive. I don't know if that's actually a word, antiderive. Okay? Let's spend some time in optimization.
Number 17.
So let's look at numbers 58.
This crap, I don't have the strength to sit up anymore.
Before we do that, I want to talk real quick about critical numbers in relation to position, velocity, acceleration. So if you are given a problem that asks you to find where an object has stopped, find when an object has stopped, what are you looking for?
Instantaneous. No.
When velocity equals 0. So in terms of what we've been doing this entire time,
Finding where the derivative equals 0.
the derivative of what function? Of a position function. So if you're being asked when an object stops, and you're given the position of that object, you have to derive and set the derivative equal to 0. If you're being asked when, we did talk about this as well, whether the object is speeding up or slowing down.
Oh yeah.
Remember that?
Well, this was like the physics.
No, Miss Crap.
Okay, so when is an object speeding up?
When
When it moves to the right.
When it's speeding up, when the second derivative.
It does involve the second derivative.
When it's
Acceleration.
It also involves the first derivative though.
Oh, when they're the different signs or something.
Something.
Signs.
Good, we're getting there. Yes, it is all about the signs. So an object is speeding up if velocity and acceleration have the same sign. Either they're both positive or they're both negative. And then it's slowing down
When it's the opposite.
when they're opposite signs. When one is positive and one is negative.
Wait. Repeat that.
Are you serious?
Yes.
Well, I guess let me fill the test.
Velocity and acceleration are different signs.
I did. I need her to repeat
So it's one of the first driven.
It's written here somewhere.
it. That's what I'm trying to do.
On a whiteboard.
On a whiteboard, which you
Yes,
can't take
on a
home.
whiteboard.
And we'll eventually get you raised.
On a whiteboard.
Oh my gosh.
Just can you repeat that, please?
Sam, if you're gonna take notes, take it on a notebook.
I know, but like really know.
Why are you writing down on a whiteboard? It's gonna get erased anyway.
Velocity.
Well, yeah, but pictures last.
No, you never.
You know what last thing is longer than that? A piece of
Velocity and acceleration.
Okay, so how do we determine that's a good question?
That
Find the
gets
derivative
crumpled
and
and written and
derivative. If it's a positive or negative, if they're different signs, then it's speeding up. They do. If the function.
actually do.
Okay. Can somebody repeat this for me? How do we know when an object is speeding up?
The velocity and acceleration is the same sign.
Okay? Did we all get that? Do you all need that to be said again?
Yes.
Repeat yourself.
When velocity and acceleration share the same sign.
What's happening at that
It's
moment?
speed up. It's speeding up.
Okay.
A particle is speeding up.
If they're
And
both.
then when a particle is slowing down, it's basically the opposite. The velocity and acceleration is decreasing.
When they
No.
what?
When they, no, that's
When they
wrong.
have different signs.
But they don't say
Yeah, different sign for
yeah.
Why, yeah, negative and negative is still speeding up.
Yeah, it's
Yeah, why?
it's negative.
Huh?
Okay, let's say this is
So that you find it's positive.
Okay, how do you determine if velocity is positive or negative?
You have to.
Find critical numbers.
And then find the means index. No,
No, the second.
find where it increases.
Logo.
No, yes.
Yeah.
You just said the intervals again?
Positive and negative between those numbers.
Like if you have like your critical numbers are 1 and 3, you look for a number here.
I think that's all I have to say about particles and critical numbers. Makes you understand that relation, huh? Okay, optimization. We have 15 minutes of class left, so I recommend you pay attention and don't make me waste time.
Like a notebook.
Just put all this down.
Probably.
You really need to.
Nobody has time for that. Quit criticizing me.
Steps to
Yeah, you pull it out real quick.
Number 58.
I hate when they do that.
Do the example on the picture with
Use pi r squared and then the thing that's wrapped around.
All right, step 1, draw a picture. There you go. That's your picture of a can.
Oh!
It's open too.
Okay, assign variables to quantities that can change. What can change for this can?
The length, the height, the width.
And the rate.
Okay, the height can change,
The width.
and the radius can change. Keep in mind, there's no top on this. Okay, I'm just showing radius up there because that's my search.
Well, it's open anyways, it's like.
That's why she said there's no top.
Step 3 is to write a formula for what needs to be optimized. What has to be optimized here?
The
The surface area of this can. So surface area is going to be what parts of this? Okay, the area of the base. How are we going to find the area of the base? Length times width. We're talking about a circle, buddy. It's a circle down here. And so we find the area of the base, which is pi r squared.
Isn't that well times 2?
No, because the top is.
No, it's plus 2h.
Oh.
Plus 2h.
Now what do we need for surface area? Okay, the area of the wraparound part. Now, yep,
Times the base?
nope.
2.
Okay, if I have, can you just listen? I have a cylinder. I'll just take this. Here's my cylinder.
Yeah.
Okay? I'm trying to figure out how much space this is. If I flatten this out, it's a rectangle. What are the 2 dimensions of the rectangle?
The diameter and the.
Circumference
And the height.
and height. So, area of a rectangle is length times width, right? So it's the circumference times the height. What's circumference?
2 pi r.
2 pi r times the height.
That's what I said.
Is it?
She said 2 pi r.
Sorry.
Explain along. It's 2 I know.
Okay. Fourth step is to write the formula in terms of one variable. What do we need in order to write this in terms of one variable?
Information.
We need other information that's been given to us. And what information has been given to us? Volume.
Volume.
How do I find volume of a cylinder? That's a cone.
Isn't that?
Pi r squared height. So I know that this is equal to 4, right? Pi r squared h is equal to 4. Which variable do I want to solve for?
Height.
Good choice. That's what I was going to say anyways. So h is equal to 4 over pi r squared.
I'll say
The purpose in doing this is so that I can plug it into the equation I want to
She's also for H, so she would probably be on that.
optimize. Last time I did this with pi in it, it got really ugly.
I know.
This one won't get ugly though. So I have pi r squared, stop talking, plus 2 pi r, and I plug in 4 over pi r squared for h. How quickly can you follow along with simplifying and deriving?
Very.
I can follow very much
Okay, you
along.
can just simplify first.
I'm good at following.
Okay, over here, pi's cancel out.
Radius.
One of the r's cancel out, I'm left with an r on the bottom. 2 times 4 is 8, so this becomes 8 over r. Can we handle that?
Yes.
So then you do for the derivative is dsa.
So the derivative in terms of radius,
2 pi r
2 pi r,
plus.
Why radius?
Oh wait, no,
Minus
minus 8 over r squared.
Minus 8 r.
Squared.
8, yeah.
Yeah.
Oh, because you moved.
Now we gotta
So 8 r to the -1. And then you
I guess the equals 0.
Did you get this? Everyone puts you get 8 pi.
derive.
The derivative.
I derive this, I bring the 2 down, subtract 1. This was r to the negative 1. I bring negative 1 down, it becomes minus. Because this can be written as r to the negative 1.
You said the middle.
This can be plus 8 r to the negative 1,
No, because it's not multiplication.
right? Huh? So then I move negative 1 down and I subtract 1, and when I subtract 1 I get negative 2. And r to the negative 2 makes it 8 over r squared.
How?
Are you tracking with that? I mean, you might show this step every time, that's fine. I'm just trying to finish before the bell rings. But that's what, you subtract 1, and then because it's a negative, you move it down. Okay, because I'm optimizing this, what am I looking for?
Common denominator.
Huh?
Oh, you're looking to find the domain of
Okay, r can't be 0, there's my domain.
finding the.
You gotta find the critical point.
Why am I finding critical points?
Because
those are where the mins and maxes are.
Okay, optimization means I'm finding a min or a max. I'm finding the best I can find, and a min or a max happens at critical numbers. So I set this equal to 0. If I get a common denominator, I just multiply this one by r squared, which gives me 2 pi r cubed minus 8 over r squared. Okay, so I just multiply this top and bottom by r squared. I set the top equal to 0.
Like this.
Oh, I did it wrong.
R cubed is going to equal 8 over 2 pi.
I reduce it to 4
then the
pi or
eight-
to cube root or 4 over pi.
Yep. So my radius for this is equal to the cube root of 4 over pi. And then I could plug that in here to get some really messy answer for you.
I got the number, like 2.3.
Because you have to
Wow,
put the
that's,
denominator.
wow, that.
This is getting messy.
At this point, I would plug this into a calculator, get a decimal answer to 4 or 5 decimals, take that answer and plug it in here to find out h. Make sure you go beyond 3 decimal places because 3 is what you need to have correct to get them right. Okay? So, for tomorrow, I've attempted, stop talking. I've attempted to cover every type of problem you could possibly see. Make sure you know how to derive. Okay, product rule, closure rule, don't forget those. Chain rule. Optimization, something like this. Those steps will be on the board tomorrow. I'm not going to take those down. You can use your notes on tomorrow's test. Keep in mind that tomorrow, well, I say keep in mind, you have an assembly tomorrow after first block during Can you stop whining and just let me get through my sentence? It's an advisory assembly. So we're going to the gym for advisory, and by we I mean like you guys, and I'll be there. But so after the assembly, get here quickly and settled quickly so that you can get started on your test. Okay, that is you being responsible students after the situation. We have press the record button at the back of that, please. Thank you.